Right, so this is the part 2 where we just summarize the first page of chapter 5 notes. So what we are doing is we are using simple Monte Carlo estimation process to find estimate of integral. So using Monte Carlo estimator, to find an estimate of an integral. So we'll start with the basic one. Consider theta equal to 0 to 1 gx dx. Right? So that's the integral that you are interested in estimating. If x1, x2, xn is a random variable which follows uniform 0, 1, then theta hat is nothing but the mean of gx. I don't need to or n, which is basically theta hat is equal to 1 over n sum gxi. I goes from 1 to n. Why? Because by strong law of large numbers, x bar n goes to mu in probability, right? So this is our mu or theta. This is our mu, and theta hat is x bar n. Think of it like that. So as n gets sufficiently large, the estimate of mu, that is x bar n, will get closer and closer to the true value of this integral. Also recall that if x is a random variable which has PDF fx, then expected value of some function of x, gx, is equal to negative infinity to positive infinity, whatever the support set is, gx fx dx. So basically you can generate from, if you know the form, you could use this technique too. We will see an example when we estimate the integrals values for normal distribution. That's where we are going to see this. But otherwise, for now, you can just generate uniform 0, 1 or uniform over AB, depending on what is the support, what is the lower and upper bound for the integral, and then you just find the expected value of that function. So to summarize, what you do is a simple Monte Carlo estimator theta equal to a to b, let's say in general gx dx, that's what you're interested in finding, is computed by using following steps. So you can think of these steps as the algorithm for which you need to convert into a code in R. Sorry, I keep getting these marks because I'm using my hand on the screen. So what you do is you generate x1, x2, xm, which is IID uniform AB. Then you compute gn x bar, which is nothing but 1 over n sum of g xi. And then because the support set is A to B, so your theta hat is B minus A G of X bar. So basically you're using change of variable. If you look at the page 1 of your notes, item 2, it says to estimate theta equal to A to B, GU or GX, whatever you want to call it, DX, DU. You use change of variable. So you have Y equal to U minus A over B minus A, and then your mu, that is your theta, becomes, or theta is equal to B minus A times 0 to 1 G of A plus B minus A Y dy. This thing is same as g of xi that you have here, and that's why you just need to multiply it by b minus a. So basically your xi is b minus a g of a plus b minus a u. So either ui, if you're calling it xi. So either you can generate from uniform 0, 1, and then you can use this change of variable technique, or you can straight up generate from generate xi's which are uniform A to B. I personally prefer to do this. It saves few steps. Why not? So you generate, because you're going to integrate from A to B, generate xi's which are uniform A to B, and then just find their mean and multiply that by b minus a, because you have to, the integral is from A to B, not from 0 to 1 anymore, right? So you'll have to do that specific step. This b minus a is basically coming from the fact that it is, when you use change of variable technique, you will get that constant of multiplication there. So hopefully this video makes things more, put things into perspective. In the next video, from the next video onward, we will do a few examples, basically filling in the blank spots in your lecture notes. So I'll see you in video number 3 soon.